Om Sri Guru Bhasvalingaya Namaha. Good morning, students. Okay, yesterday we are discussing that electrochemistry part, electrode potentials. Clear na? Reduction potential and oxidation potential during reduction, during oxidation. Based on those potentials, galvanic or voltaic cell, that is the different electrodes, different electrolytes, externally connected with voltmeter, internally connected with salt bridge, right? So, externally flow of electrons takes place from anode to cathode, internally migration of ions took place from cathodic compartment to anodic compartment through salt bridge, clear na? So, therefore, net EMF of the cell we calculated as net EMF cell equal to reduction potential at right side minus reduction potential at left side in voltaic or galvanic cell, correct? Simply higher the reduction potential minus lower the reduction potential is the net EMF of the cell, right? And after that here cell notations, cell reactions, half cell notation, half cell reaction, voltaic or galvanic cell, half cell oxidation reaction, Zn gives Zn2 plus 2 electrons at anode, whereas half cell reduction reaction Cu2 plus 2 electrons to give Cu, right? Those are half cell reactions. Cell reaction net, if you add both of them, electrons both the sides getting cancelled, thus Zn plus Cu2 plus gives Zn2 plus Cu, clear? Similarly, half cell notations, oxidation half cell notation Zn bar Zn2 plus, whereas reduction half cell notation Cu2 plus bar Cu, net cell notation Zn bar Zn2 plus double oblique Cu2 plus bar Cu. So, in that way cell notation we fixed, and according to IUPAC here electrode potentials always consider reduction potentials as standard. Therefore, if both half cells reduction potentials are given, to calculate the net EMF of the cell, higher reduction potential minus lower reduction potential, because lower reduction potential undergo oxidation, higher reduction potential undergo reduction. Therefore, reduction at right side, reduction potential at right side minus reduction potential at left side of the galvanic cell will give you net EMF of the cell if those electrolytes are standard concentrations, that is 1m concentrated. 1m concentrated electrolytes at 298 Kelvin temperature, the standard electrode potentials will be there. Those standard electrode potentials higher minus lower will give always net EMF of the cell. So, if concentrations are given, experimental concentrations are given, yesterday we covered Nernst equation. Nernst equation is what we mentioned, experimental electrode potential, this is E. Experimental electrode potential equal to standard electrode potential minus 0.0591 by n into log of products concentration divided by reactants concentration to the base 10. Correct? Here experimental electrode potential is equal to standard electrode potential minus 0.0591 by n, or this will be equal to E naught minus 2.303 RT by NF into log products concentration divided by reactants concentration to the base 10. Clear na? So, this is Nernst equation. So, in this Nernst equation, whoever this experimental concentration relation is there, this if you subtract from the standard electrode potential, then obtained electrode potential will be E, right. Suppose here whatever the here products concentration divided by the reactant concentration ratio if equal to Kc, Kc is equilibrium constant, correct. Here the ratio of products concentration to the reactant concentration ratio is Kc, Kc is what here? Equilibrium constant, equilibrium constant, okay. So, whenever this will become equilibrium, so that is at equilibrium state, experimental electrode potential will become 0. At equilibrium state, experimental electrode potential will become equal to 0, implies 0 equal to E naught minus 0.0 or else 2.303. 2.303 RT by NF into log Kc to the base 10. Correct? Either at equilibrium state, experimental electrode potential becomes equal to 0. Therefore, this above equation will become, Nernst equation will become 0 equal to E naught minus 2.303 RT by NF into log Kc. Correct? Or E naught if you bring to the left side, that is minus E naught equal to minus 2.303 RT by NF into log Kc to the base 10. Here minus minus getting cancelled, or this NF if I bring to the left side, here NF E naught equal to 2.303 RT log Kc to the base 10. Correct? So from Nernst equation what we can prove? Here NF E naught equal to 2.303 RT log Kc. Clear now? How we did? Just experimental electrode potential if you want to calculate. When it is we can able to calculate? If the concentrations of electrolytes not equal to 1 m. Experimental concentrations if there, and the temperature will be at 298 Kelvin. Under standard conditions, here other than standard conditions, experimental electrode potential if you want to calculate, this is E naught minus this difference 2.303 RT by NF into log products concentration divided by reactants concentration. If these concentrations of products to the concentrations of the reactants ratio is equal to constant according to law of mass action. Law of mass action what will say? The ratio of the product of the molar concentrations of the products to the product of the molar concentrations of the reactants is always constant according to law of mass action, Goldberg and Waage. Therefore, products concentration divided by reactant concentration is Kc, which is known as equilibrium constant at equilibrium. Therefore, at equilibrium state this experimental electrode potential will become equal to 0. Substituting this in Nernst equation and simplifying, we will get NF E naught equal to 2.303 RT log Kc. Okay. But according to thermodynamical approach, delta G naught equal to minus NF E naught. Here, delta G naught equal to minus NF E naught we know. Therefore, here NF E naught will become minus delta G naught. Substitute this value here. This NF E naught totally you substitute with minus delta G naught. Therefore, minus delta G naught is equal to 2.303 RT log Kc to the base 10, or standard free energy change equal to minus 2.303 RT into log Kc to the base 10. Correct? This is an important expression to calculate, or the relation held between equilibrium constant and free energy change. So, standard free energy change delta G naught equal to minus 2.303 RT into log Kc. Depending on Kc value, here free energy change sign will decides. So, depending on Kc value, if Kc is negative, in that case negative into negative positive, at that time the delta G naught will become non-spontaneous. If Kc is positive, then total this value becomes negative. Therefore, delta G naught will become negative, so that the phenomenon is spontaneous. If Kc equal to 0, log Kc, so if the Kc equal to 0, your free energy change value, here Kc is actually having certain values in equilibrium state. So, therefore, here depending on Kc value, delta G naught depends. Based on that, whether the phenomenon is spontaneous or non-spontaneous, we can find. Right? Suppose if they want to ask the Kc, what you can do? Here, this log Kc only here you check. Log Kc to the base 10 equal to minus delta G naught divided by 2.303 RT. Correct? Either log Kc I am keeping here only. It goes to this left side, will become the sign also enter this only. So, minus delta G naught by 2.303 RT. Now, this delta G naught if they provide, R value know in SI system as 8.314. Then temperature, standard thermodynamical temperature 298 if they provided. Then this value substitute and simplify you will get. Or Kc equal to 10 power minus delta G naught divided by 2.303 RT. 10 power minus आता आने के बाद here 10 power this log Kc is this much Kc equal to this much. This totally positive fractionals you consider with remaining the negative. So, your 10 power minus negative whole and 10 power positive fractional depending on this value. Suppose there if the Kc is 10 power minus 3.465 you got. Okay, na? The Kc value by substituting those experimental values you substitute and simplify. In that case you will get 10 power minus delta G naught divided by 2.303 RT simplification. You got minus 10 power minus 3.465. This you can write as 10 power minus 4 into 10 power 0.535. Correct? These two if you add, you will get this only, no? These two if you add, you will get this only. Therefore, your negative fractional anti-log table is not available. Therefore, positive fractional you try to consider and a negative whole number. Therefore, this you can also write 10 power minus 4 into anti-log of 0.535. Anti-log table is available. From anti-log table 0.53 under 5 if you check, you will get certain value. That value ABCD 4 digits value you will get. So, whatever the 4 digit value you will get 10 power minus 4 into ABCD 4 digit value is there. From left to right side after leaving one digit put the decimal. From left to right after leaving one digit you put the decimal. Therefore, A point BCD into 10 power, that is your Kc is equal to A point BCD into 10 power minus 4. Right? In this way you have to calculate the Kc value. So, like this NFE naught from Nernst equation, NFE naught equal to 2.303 RT log Kc, but NFE naught we know that minus delta G naught. Therefore, minus delta G naught equal to 2.303 RT into log Kc, or delta G naught equal to minus 2.303 RT into log Kc, or Kc equal to like this, or log Kc equal to like this, Kc equal to in this way. Okay, na? Like this conversion should be takes place. And one more expression already you know, delta G naught equal to minus NF E naught according to thermodynamical approach. Here E naught if negative, E naught negative, negative into negative positive, that free energy change is non-spontaneous. If E naught is negative, it is total delta G naught positive is non-spontaneous. If E naught is positive, at that time delta G naught will become negative, it is the spontaneous. If E naught equal to 0, delta G naught also becomes equal to 0, the system is in equilibrium. Right? Like this, whoever the values they provided, according to the values, free energy change or E naught or number of moles of electrons or Kc or experimental electrode potential, what they are going to ask, that information you have to simplify from these expressions. Right? This is Nernst equation application. Okay? Electrode potentials, then redox reactions, electrode potentials में net EMF of the cell, galvanic or voltaic cell, here chemical energy get converted into electrical energy, and anode is with negative sign, cathode is with positive sign, flow of electrons from anode to cathode, flow of current from cathode to anode, then migration of ions from cathodic compartment to anodic compartment, at anode oxidation, whereas in anodic compartment reduction, at cathode reduction, whereas in cathodic compartment oxidation. So, all that information already we did yesterday, right? So, this is about electrochemical cells. Next, electrolytic cells let us see. electrolytic cells. Electrolytic cells, here one electrolyte, two different electrodes, one is connected to anode, other is connected to cathode of the battery. It is with negative sign, it is with positive sign, it is an electrolyte, whereas it is cathode and it is anode. Okay, na? So anode and cathode are externally connected to battery. This is the battery. Now in case of electrolytic cells, anode is with positive sign, electrochemical cell anode is with negative sign. Here in electrolytic cell cathode is with negative sign, electrochemical cell cathode is with positive sign. Clear na? So with the help of battery, if we pass certain quantity of electricity through electrolyte with the help of electrodes, observe carefully, when we pass, here what we are doing, with the help of battery we are passing an electricity, with the help of battery we are passing an electricity through electrolyte. At that time certain phenomena is taking place. In electrochemical cells what will be taking place? Electrode, metal electrode itself undergo oxidation, then respective other electrode undergo reduction, thus the chemical energy converted into electrical energy. Whereas here through electrolyte certain quantity of electricity we are passing, right? Certain quantity of electricity we are passing through with the help of battery through electrolyte, then certain phenomena are taking place. On that Faraday studied and Faraday told Faraday's first law. Faraday's first law, if you consider, according to this, the amount of the substance which is deposited or liberated or ionized at their respective electrodes depends on directly proportional to quantity of electricity passed through an electrolyte during electrolysis. देखो इधर the amount of substance, deposited if it is metal or liberated non-metal, the amount of the substance deposited or liberated or even ionized, the amount of the substance deposited or liberated or ionized at their respective electrodes, depends on directly proportional to see the amount of substance deposited or liberated or ionized at their respective electrodes depends on directly proportional to quantity of electricity passed through an electrolyte during electrolysis. See, definition concept you must know. What will be given here? The amount of the substance which is deposited or liberated or ionized, that is mass. Correct? Mass of the substance which can deposit or liberates and ionized at their respective electrodes depends on directly proportional to quantity of electricity passed through an electrolyte. M is directly proportional to Q, but quantity of an electrolyte Q equal to IT. Some books will mention it is CT. Q equal to IT, where I is strength of current, Q is quantity of electricity. Quantity of electricity is in coulombs, whereas strength of current is in amperes. Therefore, this mass of the substance depends and directly proportional to I into T na, Q equal to IT, therefore M is directly proportional to IT, or either M equal to some ZQ, similarly M is also equal to some ZIT, okay na? Z here electrochemical equivalence, Z is what? Electrochemical equivalence, or Z equal to mass by Q, or here Z equal to that mass by IT. Clear na? Suppose Q equal to 1, when the quantity of electricity passed through an electrolyte is fixed as 1 coulomb, at that time whatever the mass of the substance which is deposited or liberated is equal to its electrochemical equivalence. Similarly, during 1 second time, 1 ampere strength of current is passed through an electrolyte. Electrolyte say 1 ampere strength of current is passed during 1 second time, whatever the mass of the substance deposited or liberated is known as electrochemical equivalence. Correct? Here you can also write if Q equal to 1 coulomb implies the deposited mass is equal to electrochemical equivalence. Similarly, if T equal to 1 second and I equal to 1 ampere, okay na? 1 second time 1 ampere strength of current is passed, then that implies Z equal to M. Nothing but the amount of the substance which is deposited or liberated when 1 ampere strength of current is passed during 1 second time through an electrolyte is called electrochemical equivalence, or else when 1 coulomb quantity of electricity is passed through an electrolyte, then the amount of the substance which is deposited or liberated is called electrochemical equivalence. Therefore, here the terms evaluation, if you come here, M equal to mass of the substance, mass of the substance, mass of the substance is in grams, Q quantity of electricity, quantity of electricity, quantity of electricity is in coulombs, C stands for coulombs. Then I equal to strength of current, strength of current in amperes, T equal to time, that is in seconds, Z equal to electrochemical equivalence, electrochemical equivalence, electrochemical equivalence in gram per coulomb or gram per ampere into second. Correct? Here Z is electrochemical equivalence, gram per coulomb or gram per ampere into second. So this is the Faraday's first law, and Faraday's first law simply, Faraday's first law what it will tell, the amount of substance which is deposited or liberated during electrolysis depends and directly proportional to quantity of electricity passed through an electrolyte during electrolysis. Correct? वो electrolysis time पे electrolysis phenomena ने इधर कितना quantity of electricity हम pass कर रहे हैं, based on that the metallic ions who are present in that electrolyte deposit as its mass. So the amount of the substance which is deposited or liberated generally or sometimes ionized depends and directly proportional to quantity of electricity passed through an electrolyte during electrolysis. These are possible expressions, right? They may ask M by giving Q, they may ask I by giving Q and T, they may ask even I by giving Q and M, Z they may ask. So based on this, here what they given, what they are asking, then given data select karo, after that a proper expression, mathematical expression you can choose and decide. Okay na? Generally here problems in what way will be there? Suppose 1 mole of electrons are passed. Here through an electrolyte, if 1 mole of electrons, 1 mole of electrons, that is 6.023 into 10 power 23. 1 mole of electrons are passed through an electrolyte. The quantity of electricity is equal to 1 mole of electrons, that is 6.023 into 10 power 23. Number of electrons responsible for 1 Faraday quantity of electricity. 1 Faraday quantity or 96,500 coulombs quantity electricity. See, 1 mole of electrons, that is flowing of 6.023 into 10 power 23 number of electrons are responsible for 1 Faraday or 96,500 coulombs quantity of electricity. In what way? Here charge of electron equal to some 1.6 into 10 power minus 19 coulombs. Correct? Therefore, for 1 mole, the quantity of electricity, for 1 mole, the quantity of electricity is equal to 6.023 into 10 power 23 into 1.6 into 10 power minus 19 coulombs. If you simplify it, you will get 96,500 coulombs are approximately equal to 1 Faraday, since 1 Faraday equal to 96,500 coulombs. Okay, na? 1 Faraday quantity is how much? 96,500 coulombs, which is equal with 6.023 into 10 power 23 into 1.6 into 10 power minus 19. If you multiply this, you are going to this as a coulombs quantity of electricity. Then under this is total given by Faraday. Therefore, under Michael Faraday name, that 96,500 coulombs is equated to 1 Faraday. Right? So problems में कैसा कर सकते हैं इधर? Suppose calculate the amount of so and so metal deposited. This is some standard statements to do the problems. Okay, na? Suppose find the mass of silver deposited when so and so coulombs quantity of electricity is passed through silver nitrate electrolyte. Say find or calculate, find the mass of silver deposited, find the mass of silver deposited when 965 coulombs quantity of electricity find the mass of silver deposited when 965 coulombs quantity of electricity is passed through silver nitrate electrolyte. So here silver nitrate electrolyte is important cause say. So you know silver nitrate get ionized to give Ag plus plus NO3 minus. Correct? Silver nitrate electrolyte get ionized into Ag plus plus NO3 minus. Therefore, Ag plus, through which how many moles of electrons are flowing? 1 mole of electrons are flowing, right? To deposit how many moles of silver? 1 mole of silver. 1 mole of silver is 108 grams. Atomic mass of silver is 108 or 107.9 grams, right? So 1 mole of electrons flow is responsible for how much quantity of electricity? 1 mole of electrons, just now we calculated, 1 mole of electrons 6.023 into 10 power 23 into 1.6 into 10 power minus 19 coulombs, correct? Therefore, 1 mole of electrons flow responsible for 96,500 coulombs quantity of electricity. See here 1 mole of electrons flow is responsible for 96,500 coulombs quantity of electricity, correct? Quantity of electricity. This you come to know. Here 1 mole of electrons flow is responsible for 96,500 coulombs quantity of electricity. Suppose here 2 moles of electrons are flowing. Here some Cu2 plus is there. Cu2 plus 2 moles of electrons. Al3 plus 3 moles of electrons. So here how many number of moles of electrons are flowing? See that number into 96,500 coulombs quantity of electricity. Correct? So this statement you come to know. Therefore 96,500 ओना बोले तो 1 into 96,500 coulombs लेव 1 into 96,500 coulombs nothing but 1 mole 1 into 96,500 coulombs quantity of electricity deposits 108 grams of silver, correct? 108 grams of silver. Very simple. Here first given electrolyte ionization you have to check. After ionization what charge densities are got and according to the charge density how many moles of electrons are flowing. 1 mole of electrons flow responsible for 96,500 coulombs quantity. Then here 1 mole is this much. Suppose here 2 moles 2 into, 3 moles 3 into. So 1 into 96,500 coulombs quantity of electricity deposits 180 grams of silver. Then experimentally 965 coulombs problem में दिए. So for 965 coulombs quantity of electricity, how much mass of silver is depositing? Therefore, mass of silver is equal to 965 into 108 divided by 96,500. It is 100 times. So 1.08 grams of silver deposits. Clear na? 1.08 grams of silver depositing. In this way we have to do. So first electrolyte. What electrolyte is given? How it get ionized? Those ions, if it is cation, moves toward the cathode. Anion moves toward the anode. During migration of those ions toward their respective electrodes, how many moles of electrons are flowing? Based on that number of moles of electrons, number of mole into 96,500 coulombs quantity, number of mole into 1 Faraday quantity of electricity is going to pass. Then for experimental quantity, how much is going to deposit? In that way you have to do. Okay, na? Here this is actually basic concept. From this basic concept, link based they may ask. Here calculate the volume of oxygen and hydrogen liberated during electrolysis of acidylated water. Acidylated water, nothing but water electrolysis करे तो oxygen और hydrogen liberate होता. That liberated oxygen and hydrogen for certain standard quantity of electricity passing, you know, experimental quantity of electricity if we pass, then how much volume or how much mass or how many moles of hydrogen and oxygen liberating at the respective electrodes. Here suppose volume, if I ask calculate the volume of hydrogen and oxygen liberating calculate the volume of hydrogen and oxygen liberated when 0.5 ampere strength of current passed through acidulated water. Check karo here. Calculate the volume of hydrogen and oxygen liberated when 0.5 ampere strength of current passed through acidulated water during 10 minutes time. Okay, na? Here what will be given? Given data is what? Given data I equal to 0.5 amperes, then T equal to 10 minutes. 10 minutes we have to convert into seconds. 10 into 60, 600 seconds. Correct? 600 seconds. This you know. Therefore, IT equal to Q, which is equal to 0.5 into 600 is equal to 300. 0.5 is 1 by 2. 600 into 1 by 2. 600 by 2 is 300. 300 is what? Coulombs. This is experimental quantity of electricity. Clear na? Here acidulated water get ionized into H plus plus OH minus in acidic medium. That OH minus further ionized into H plus and O2 minus. Correct? So, OH minus both the sides getting cancelled. Thus, 1 mole of H2O get ionized to give 2H plus and O2 minus. This is ionization. Correct? During this ionization, O2 minus moves toward the anode by giving 2 electrons as half mole of oxygen liberating. Oxide moves toward the anode, giving 2 electrons to anode, liberates 1 by 2 moles of oxygen. Correct? Similarly, here 2H plus takes those 2 electrons and liberates 1 mole of hydrogen at cathode. At cathode 1 mole of hydrogen is coming, at anode half mole of hydrogen oxygen is coming. But here during anode and during cathode, how many moles of electrons are flowing? 2 moles of electrons are flowing. Standardly 2 into 96,500 coulombs quantity of electricity is passing. Therefore, here what you know? 2 into 96,500 coulombs quantity liberates 1 by 2 into 22.4 liters of oxygen. Correct? 1 by 2 into 22.4 liters of oxygen. Then 300 coulombs quantity is how much? Therefore, volume of oxygen is equal to 300 into that 1 by 2 into 22.4 divided by 96, 2 into 96,500. Correct? Now, here 2 11.2s are 2 5.6 are. Therefore, here 2 zeros getting cancelled. 3 into 5.6 divided by 965 or 3 6 are 18, 1 3 5 are 15, 1 16.8, 16.8 divided by 965. You can simplify and you are going to get. So, volume of oxygen equal to 16.8 divided by 965. How much you are going to get? That liters or into 1000 milliliters of oxygen is going to get. Similarly, if you come to here again 2 into 96,500 coulombs liberate 22.4 liters of hydrogen. Correct? 1 mole 22.4 liters. Then 300 coulombs quantity how much? Therefore, volume of hydrogen equal to 300 into 22.4 divided by 2 into 96,500. Therefore, 11.2. ये दोनों getting cancel. Now, 33.6 divided by 965. Either 16.8. 16.8 2s are 2 8s are 16 1, 2 6s are 12 1, 13 1, 2 1s are 2 plus 1 3. Nothing but 2 times. So you will get the volume of hydrogen is 2 times the volume of oxygen. If you simplify, you will get the volume of oxygen as well as volume of hydrogen at that STP conditions. So in this way, here first of all what you have to check, whatever electrolyte is there, how that electrolyte get ionized. During that ionization, how many moles of electrons are participating with respect to the number of moles, that into 96,500 coulombs quantity, or else that into 1 Faraday quantity of electricity is going to pass. With respect to that, here how much volume, how many moles, half mole of oxygen or 16 grams of oxygen or 11.2 liters of oxygen. Then for experimental, I and T given, I and T, I into T is Q, therefore I into T Q already we calculated as 300 seconds. So for 300 coulombs, and for experimental coulomb quantity of electricity is how much volume, then you can get like this. Clear na? In this way, here what they are asking, number of moles they are asking, or mass they are asking, if gas, if volume they are asking. So like that you check, and from electrolyte, this equation compulsory you should in a position to frame. During ionization, how many moles of electrons are flowing through electrolyte, that also you find that number of moles of electrons into 96,500 coulomb quantity is a standard quantity. With respect to that, how many moles are coming, how much mass is coming, how much volume is coming, that you decide, and experimental quantity how much. Clear na? So like this, Faraday's first law, and so many varieties of problems they may give. And Faraday's second law. Faraday's second law, what it shows, when same quantity of electricity is passing. See here, Faraday's second law. Faraday's second law, this is an electrolyte, it is another electrolyte, and like this in series different electrolytes if we arranged, it is first electrolytes, 2 electrodes are dipped, second electrolyte, 2 electrodes are dipped, third electrolyte, 2 electrodes are dipped. Like this, different electrolytes and different electrodes we dipped, and these electrodes are connected to battery. Like this, these electrodes are connected to battery. Now, these are connected in this way, and these are also connected in this way, right? Here electrolyte 1, electrolyte 2, electrolyte 3. So different electrolytes if are there, through the different electrolytes, here how much quantity of electricity we are going to pass. Depending, same quantity of electricity when we pass through the different electrolytes who are arranged in series, through the different electrolytes who are arranged in the series, through them same quantity of electricity if we pass, then amounts of the substances which are deposited or liberated are in the ratio of their equivalent masses. Suppose here for our example NaCl, here MgCl2, here AlCl3, like this electrolytes if you take, this NaCl get ionized into Na plus plus Cl minus. Therefore, Na plus an electron is 1 Faraday quantity of electricity, will deposit 23 grams of sodium. Here it get ionized into Mg2 plus Mg2 plus 2 Cl minus, 2 Cl minus. Therefore, Mg2 plus through which 1 mole of electron, because 1 Faraday quantity will give Mg plus, with respect to that it is 12 grams. Here it get ionized into Al3 plus 3 Cl minus. Here also 1 Faraday quantity of electricity when we pass, Al3 plus an electron gives Al2 plus 9 grams. Okay, na? 9 grams going to deposit. Therefore, here 9 grams. Now 23 grams is an equivalent mass of sodium. 12 grams is an equivalent mass of magnesium. 9 grams equivalent mass of aluminum. Correct? These are actually original masses. The original masses who are depositing, that is mass of sodium is to mass of magnesium is to mass of aluminum is equal to equivalent mass of sodium is to equivalent mass of magnesium is to equivalent mass of aluminum. Correct? Here the amounts of the substances which are deposited or liberated at their respective electrodes are in the ratio of their equivalent masses. Or you can also write mass of sodium divided by mass of magnesium is equal to equivalent mass of sodium divided by equivalent mass of magnesium, or mass of sodium divided by mass of aluminum equal to equivalent mass of sodium divided by equivalent mass of aluminum, or mass of magnesium divided by mass of aluminum is equal to equivalent mass of magnesium divided by equivalent mass of aluminum. Like this we can consider. Correct? So here what we can say, Ma is to Mb is equal to Ea is to Eb, or Ma divided by Mb is equal to Ea divided by Eb. Clear, na? So what is this definition? When the same quantity of electricity, when the same quantity of electricity, when the same quantity of electricity is passed through, when the same quantity of electricity is passed through different electrolytes, when the same quantity of electricity is passed through the different electrolytes which are arranged in series, okay, na? When the same quantity of electricity is passed through the different electrolytes which are arranged in the series, then the amounts of the substances, which are deposited or liberated, which are deposited or liberated, are in the ratio of their equivalent masses, are in the ratio of their equivalent masses. Okay, na? So this is the Faraday's second law. Faraday's second law shows what? The amounts of the substances which are deposited or liberated are in the ratio of their equivalent masses when same quantity of electricity is passed through different electrolytes during electrolysis. Okay, na? So in this way we can decide the Faraday's second law. According to Faraday's second law, we can also calculate equivalent masses of unknown metals. Unknown substances equivalent masses we can calculate. Clear, na? So this information, electrochemical cells and electrolytic cells, one more time revision I did. If you need in this lesson one more conductance, conductors are there, conductance. So that conductance one more class if I discuss, conductance is going to complete. And some students asked me equilibria, ionic equilibria, and some students asked stereochemistry, right? Organic chemistry, stereochemistry. Suppose from this electrochemistry remaining part, if we will definitely prepare, sir, if you have the confidence, let me start the stereochemistry. Okay. If you need stereochemistry part, I will discuss, and if you need ionic equilibria, I will discuss along with the remaining part of electrochemistry. So, whatever it may be, during these days I will come to know from some students. So, those students which kind of information they are going to ask, that I will discuss on next, that coming Tuesday 27th. Okay, na? See, all the best, and I wish you all